It's my pleasure to introduce Pat Verga from the University of Massachusetts. Pat is a final year PhD candidate working with Andrew McCallum's group at UMass. He does work in the area of knowledge representation, information extraction, and natural language processing. Publishes in august places like ACL and EMNLP. He's the winner of the Best Paper Award at EMNLP 2018. He's done internships at Google and the Chan Zuckerberg Initiative, which I'm not sure what that is. But
it's like the Mark Zuckerberg philanthropy where he throws his money away. Yeah, which is nice stuff.
Today he's going to talk to us about some of his thesis work on neural knowledge representation and reasoning.
Great. Thanks. All right, thanks for the introduction, and thanks everyone for coming out. So today I want to present some methods for representing knowledge in a way that's going to both aid the acquisition of new knowledge and also help facilitate higher level reasoning. And the way we're going to do this is by integrating neural architectures with structured ontologies. So in our world today, we need to be able to make complex decisions. We need to be able to make complex decisions in areas that include government policy, finance, biomedical research, and clinical treatments. And to make the most informed, data-driven decisions means integrating and reasoning over many different sources of information. So sometimes this analysis is about directly processing some observed data. So for example, this could be identifying particular entities in an image. So in this case, the presence of cancer cells. And in other situations, we may want to select a slice from a larger set of data that we can then run some further analysis on. So this could be the case in something like document retrieval or search. However, other times we want to be able to directly produce an answer from a massive set of data. So for example, given this query, we want to know what's the specific entity that's going to answer our question. So recent methods in text-based question answering systems have successfully learned to extract answers directly from text alone. And when a question can be answered from a single piece of evidence, these methods have shown really impressive results. However, currently these models are still a bit limited in terms of reasoning about many sources of information at once. So for example, there are cases where an answer to a question can't be found in a single document, but instead it requires reasoning over multiple pieces of evidence through multiple steps of reasoning. This can also be the case when disambiguating the meaning of a particular concept is going to require integrating background knowledge. So another approach to answering these questions is by reasoning over a knowledge base. So knowledge bases are really a natural way of integrating information from many heterogeneous sources, which could include text and databases. And what a knowledge base, or synonymously a knowledge graph, actually is a graph that's going to represent concepts and entities as nodes, and it's going to represent the relationships between those concepts as edges. So we can have some method that will align our query with some subset of the knowledge graph, and we then reason about the neighboring concepts and the relations between them to arrive at some potential answer to our question. And importantly, the evidence for these different edges are going to be coming from different sources. And again, this is really one of the biggest benefits of a structured knowledge base like this, is it allows us to naturally integrate information from various sources in this unified and easily computable abstract representation. So at this point, knowledge graphs are widely used in many of the big tech companies. So for example, the Google Knowledge Graph contains general knowledge to help in search and question answering. Bloomberg uses knowledge bases to organize companies and financial information. And Amazon uses knowledge graphs to organize and recommend all the products on their site. So the graphs that we're talking about so far all have their semantics defined symbolically. But this can really lead to a few issues. So the first is, how exactly are we going to define our ontology? And what I mean is, what are the possible types that the nodes and the edges can actually take on? So for example, in some applications, you may classify the concept Alagille syndrome as a disease, but in other applications, you would benefit from in other applications, you might require a finer grain analysis, and you'd benefit from a more specific type like genetic disorder. And in other applications, you may have the opposite problem. So maybe there's some data sparsity and beta receptor blocker is just too specific of a type. Instead, you get better results if you just treat this concept as a disease or as a drug. And the same applies for edge types as well, where maybe instead of the relation type leads to, we'd rather represent a finer grained relationship between these two concepts. So deciding what the graph's ontology should consist of is an important problem to consider. And again, that is, what are the possible types that the entities and the relationships can actually take on? Because ultimately, this is what's going to define the limit on the possible semantics that we're going to be able to represent. So in the rest of the talk, I'm going to discuss various methods for representing these graphs with embeddings, and using not just predefined structured ontologies, but also modeling additional types that are expressed in unstructured text itself. So I just want to briefly outline the contents of the talk so that you get a sense of where we're going to be going. So first, I'm going to go through a little bit of the background on methods for building and representing knowledge graphs that is going to serve as the basis for much of the rest of the work I'll present after that. Next, I'm going to talk about several of the projects I worked on during my PhD. So this has included expanding the generalization of some of these models with compositional embeddings, methods for improving the representation of entities and their types by embedding their hypernym hierarchies, and two different approaches for representing knowledge and context. And lastly, I'm going to present some ideas of future directions for cognitively inspired models that can expand on all of the work that I will presented up to that point. So far we've just been talking about this biomedical domain, but these methods are really applicable to most any domain. And for ease of intuitive understanding, I'm going to transition to the more general domain of people, places, and organizations. So again, we're still talking about knowledge graphs, where here nodes represent concepts and entities, and the edges are representing relationships between those concepts. So how do we actually get a knowledge graph? In reality, these graphs are typically filled with hand-curated facts existing within some fixed, predefined schema of node and edge types. But this hand curation inevitably leads to high levels of incompleteness because it's not actually feasible to write down all of the possible facts. So what we'd really like is a way of automatically building these graphs. So the goal of automatic knowledge-based construction, or AKBC, which you can kind of see up there, is to go from a corpus of unstructured text to a knowledge graph of entities and their relationships. And to actually accomplish this takes a few steps. So first, we're going to find all of the mentions in our documents of the entities and the concepts that we're interested in. So in this case, we're going to find all of the people, places, and organizations. And next, we're going to need to link together mentions that are referring to the same entity. So here we have 4 mentions that are referring to the same entity, Bill Gates. And so this is an important distinction to keep in mind because we're going to be talking a lot about entities versus mentions in the rest of this talk. So every time you see Bill Gates written in text, those are mentions, and they're all referring to the same single entity, which is the concept that is Bill Gates. So we can do the same procedure over our whole corpus and collect all of the entities and co-occurring entity pairs that we find. And since we also want to be able to say something about the meanings of these entities, we're also going to have a set of types that the entities and their relationships can actually take on. And often we aren't really going to be starting from scratch, but instead we can start from some initial incomplete human curated knowledge base as a starting point. So first we can consider the human defined types as an initial set to define the semantics of our entities and our entity pair relationships. And as we talked about earlier, the schema itself is going to suffer from the same type of incompleteness as the knowledge graph. So some human pre-decided what are the set of possible types that would define all of the semantics that we'd ever want to consider, but inevitably this isn't going to cover everything. But if we instead look at the text directly, we can find textual types that are going to express really a limitless amount of fine-grained and expressive entity and relation types. And these would never necessarily exist in a curated schema. So what I'm describing here is a universal schema which jointly considers structured and unstructured types in a unified ontology. Okay, so for now, let's just look at these entity pair relationships. So at this point, we have this massive binary co-occurrence matrix. And here, a green cell is depicting a fact that we observed in our training data. So for example, this green cell is denoting the fact that Obama was the President of the United States. But how should we actually represent these entities and their types? And how can we do it in a way that we can capture the semantic similarities between them? Because ultimately we want to be able to predict new relationships that we didn't directly observe. So one way we can do this is with embeddings. So what we can do is represent each row and each column of this matrix as an embedded vector. And one way to learn the parameters of these embeddings is just to factorize this co-occurrence matrix. So to start with, all the vectors will be initialized to random values, and then we can select a positive cell that we observed in our training data, as well as a random unobserved cell that we can assume to be negative with high likelihood. And then the objective is just to make the score of the positive cell higher than the score of the negative cell. And here the score for each cell is going to be a function of the row and column vector. For example, it could be a dot product between the two vectors. And to think about intuitively what's happening here is that we're updating the values of our vectors such that positive training pairs are being pushed closer together and negative pairs are being pushed farther apart. And then throughout the course of training, we just want to find what is the best setting of these parameters such that overall positive things are closer together and negative ones are farther apart. And eventually we're going to have this unified embedding space of both structured types and also unstructured types that are coming directly from the text itself. And then relationships that are expressing similar semantics are going to be clustered in similar regions of this embedding space. Okay, so now that we've gone through the background materials, I'm going to go through some of my own work. And to start with, I'm going to discuss a method to improve the generalization of universal schema. So what I just described is a model from the original universal schema work, but unfortunately in its original form it has a few shortcomings. So the first is that there's actually no sharing of information amongst very similar types. So for example, you could have something like born in and born in the city, and both of these types are going to be represented as their own columns in our matrix, and therefore have their own completely distinct vectors. And the other issue is that this model is actually unable to make any predictions about types it didn't explicitly see during training time. So if you have some new document containing some new sentence, we don't have any learned vector representation for this column, and we won't be able to make any predictions about the meaning of this text. So to address this, we replaced this explicit column parameterization with some learned neural text encoder that's going to map arbitrary text into a vector that exists in the same embedding space as our other column vectors. And then we can use these embeddings to make new predictions about what's the meaning of this particular piece of text. So this encoder is really, you can just think of it as a function that's going to map a piece of text to a single vector, which is encoding the semantics of that piece of text. So you can kind of just think about that. But for concreteness, in our first work, we used an LSTM to contextually encode context-independent token embeddings. And then to get a single vector representation over the entire sentence, we perform a max pooling operation. So this is just for each of the k dimensions of our vectors, the output of that dimension is the maximum value over the inputs for the corresponding dimension. But again, you can just think of this as some function that's going to map a piece of text to a vector for the purposes of this talk. So one really interesting property is that we can actually map any language into the same embedding space. So we can have some columns that exist in English, some in Spanish, some in Russian, and so on and so forth. And because we're going to have shared entities that exist in all of these languages, the different languages are going to be aligned by our model.
Could you speak up just a little bit?
Oh,
Speak up a little bit.
Sure.
Or can you use mine? We don't have a light to the room. Oh, light to the video. Okay.
I'll try to just be louder. Is it?
The sound is lost in the room.
I see. Well,
The mic is only for the video, so it doesn't. So
Just speak up a little louder.
You can
that's
move
all.
your chairs up to the
Yeah.
front if you want.
yeah.
There's a couple seats up here.
Okay. So in this particular example, we can see that Melinda and Bill Gates are entities that exist in all three languages. And all of these different languages are being pushed together and aligned and anchored by these shared entities. So at the beginning of training, all of our languages are going to have their own disjoint embedding spaces. And the assumption we're making is the same as in many multilingual embedding methods, that the underlying semantic spaces of the different languages are going to be roughly the same shape and exhibit the same underlying semantic properties. And then over the course of training, these shared entities are anchoring specific points of the spaces, causing each language to align overall. So we can take a look at some of the outputs produced by one of our models. So these are coming from a large model which we trained on about a dozen languages. So on the left, we'll have an input from a non-English language, and on the right, we could see some of the most similar English patterns that the model found. So we see things like capital of in Spanish being mapped correctly to capital of in English, was elected president, similar to things like re-elect, love eating being similar to munch, and married being similar to unite with. And we also use this model as the basis for our system in the DARPA TAC KBP competition. And the setting of this shared task is just given a corpus, construct a knowledge base. So our system was ranked first in the 2016 Spanish KBP competition, and we even showed that we were able to perform relation extraction in Spanish using only supervised data in English. And additionally, this is the top system on the Stanford KBP leaderboard, which is another evaluation on this TAC data. So now that we've talked a bit about embedding entities and their relationships, I actually want to show how we can improve our embedded representations further by explicitly modeling hypernym relationships between the types themselves. So let's look back at our entity type matrix. So here the rows are individual entities, and the columns are types that those entities can take on, such as person, location, and politician. And so far we've been treating these column types as a flat set, but in reality, these types exist in this rich hypernym hierarchy, such that a president is a politician and a politician is a type of person. And we'd like to be able to leverage this additional structure to improve our models further. So just as before, each of our types can be represented by a single vector. But now we're going to enforce this additional constraint on our embedding space that it should respect this type hierarchy. And the way we're going to do this is by training a function that's going to give high scores for edges that actually exist in the hierarchy, and then just low scores for edges that don't exist in the hierarchy. Hey.
What do you do for two-step edges, so like president to person?
Mm-hmm. President to person. Right, so we can have an additional edge. Oh, I actually have a laser. So we can have like a is a link connecting these two and treat that as an individual edge. All right, so in our work, we looked at two different functions that have been widely used to embed knowledge graphs in the past. So the first is this bilinear scorer. So here, we're going to model this is a edge as a D by D matrix. And the score for any particular edge is just the bilinear product between the two types and this is a matrix, which will give us some scalar value. And the second function that we looked at was a complex bilinear. So in this model, the types and the edges have complex valued vectors. And we can represent these as two vectors, one real and one imaginary. And then the overall hypernym edge score is just the Hermitian dot product between the two types and the is a representation. It is really just a dot product between complex valued vectors. It is a way for us to model these asymmetric relationships. So what we really like is, given some new sentence, we want to map the entity dimensions to vectors whose representations are going to fall on the appropriate spot in the hierarchy. So here, Melinda Gates should represent that she's a founder and a person, and the foundation should show that it's a nonprofit organization. And we can score these mentioned type pairs with the same function that we're using to score the other edges in our hierarchy. And in this way, the text mentions and the types are treated in the same way, and they're going to exist in the same space that embeds the hierarchy. So the first results I'm going to show here are on this data set FIGER, which is the most widely used data set for this particular task, which is called fine-grained entity type prediction. So we can first see that our base model, which is a convolutional neural net in this case, is performing similar to comparable previous state-of-the-art methods. But most interestingly, our type-aware hierarchy training actually improves the results quite substantially over the model treating the types as a flat set. And our best model is even comparable to a much more complex one, which used a lot of external resources and additional features. So even though we were able to show that explicit hierarchy modeling could improve our methods, in reality, this Feiger type hierarchy is actually very small. So it contains only 121 types with a depth of 2. And this really limits what we can represent in terms of both the breadth of the type semantics as well as the relationships between the types. So to further probe our model and also to help advance research in this direction of hierarchical type modeling, we wanted to create a bigger, deeper type hierarchy. So we came up with TypeNet, which is a manual alignment between freebase types and WordNet synsets. And this new type set consists of about 2,000 types and has a maximum depth of 14. And we could take a look at a few examples of the structure of TypeNet, where we can see very fine-grained types like Olympic host city, different foods like cheese, and particular types of athletes. And they all have kind of rich hierarchy structure. And the way we evaluated our models on TypeNet is a bit different. So in this case, we don't have direct labelings from individual mentions to individual types. Instead, we only know that this particular mention contains the entity Melinda Gates, and Melinda Gates has some set of types that are going to describe her. So now the problem is instead to map this set of text mentions containing Melinda Gates to the set of types that we know she should have. And we can think of this as entity-level type prediction as opposed to mention-level type prediction. So again, mentions are individual sentences, and entities are kind of the whole concept of Melinda Gates. So the way we're going to do this is to first map each mention to a single vector, in this case using a convolutional neural net. And then we're going to score each mention against each of the types in our whole type set. So here I'm only showing the positive types for this particular example, but in reality we're going to score amongst the full set of 2,000 types. And this is going to give us our mention level predictions. We're then going to aggregate all of these mention level scores together using some pooling function, and this is going to give us a single set of predictions, which will be our entity level predictions for Melinda Gates. All right, so what we find is that using our hierarchy actually substantially improves our results overall. So our best model is even 10 points of accuracy higher than the equivalent model that treated the types as a flat set. So we're also really interested in using these same methods for other domains. And in particular, we're interested in this biomedical domain. So to help us do this, we first wanted to create a rich data set of text that was annotated with biomedical entities that we call med-mentions. So here's an example of 2 titles and abstracts from biomedical research papers. And we got expert annotators to identify occurrences of genes and diseases, pharmacological substances, biofunctions, proteins, as well as several other types. And in addition to identifying the mentions of these particular entities, we also had them link the mentions to the correct entity in the UMLS knowledge base. And it's particularly nice because UMLS arranges their entities in this very rich hierarchy. So this data set was about an order of magnitude larger than some of the previous comparable data sets. And in entity linking experiments on med-mentions, we again found that modeling the hierarchy improved the performance of our models. And there's more details in our paper if something you're interested in. Right, so we've been talking a lot about knowledge graphs and how they encode information about entities. And one property about these graphs that can actually end up being detrimental in some cases is the fact that we're encoding knowledge at an abstract level. So what I mean by this is that the information isn't necessarily grounded in any particular instance or piece of data, but instead we're encoding some global notion about the entities. And because we're doing this, we can end up in a situation where the graph can actually contain seemingly contradictory information, such as a chemical that both treats and causes the same disease. And when you go and look at specific instances of these entities, you can see, for example, that in one paper they found that this drug did treat this disease. But in a second paper, they said the drug actually can cause the same disease. And importantly, it's not even the case that one of these facts has to be wrong, because in the end, both can actually be true, but they can be true in different contexts. So for example, if we're talking about in the context of rats or the context of humans. And I think this notion of how we can represent knowledge in context is really extremely important for advancing knowledge representation research going forward. So I'm going to talk a bit about a few initial steps in this direction before going on to talk about how we can take these ideas even further in the future. All right, so next I'm going to talk about 2 projects for representing knowledge in context. So in our model, our entity representations so far have been a single vector. And having an entity as a single vector is really encoding some abstract, generic notion of that entity. But these entities can really appear in much different contexts. And when we're considering really fine-grained types, these contexts could encode very different semantics. So an alternative approach to a single vector that would allow us to capture these different contexts is to instead consider the individual mentions of the entities themselves. And each of these mentions is going to exhibit different types. So what we can do is actually represent entities as some function over the individual mentions themselves. So in our work, we investigated a few different functions for actually doing this aggregation over mentions. So the first 2 are query-independent functions. So these are going to generate the same representation for an entity, regardless of any particular query we're trying to answer. So the first is just a simple averaging over the observed mentions. And the second is a max pool, which again takes the maximum value at each dimension over the mentions. All right, and the second class of functions we looked at were query-dependent ones. So here we're going to aggregate the observed types differently depending on what query it is that we want to answer. So if we had a query like, is Melinda Gates a board member of an organization, we could first calculate some similarity score between a representation of the query and each of the observed mentions. And for example, this could be a dot product between the 2 vectors. All right, and in this max column method, the prediction is going to be made solely by the most similar observed mention. So here, founder is going to be predictive evidence that Melinda Gates could be a board member. And the second query-dependent method we looked at was an attention-based one. So here we're going to take a weighted average over all of the observed mentions relative to their similarity to the query. And it's worth noting that while founder doesn't always directly imply board member, in this scenario we're working with soft evidence and uncertain predictions to just estimate how likely the query is to be correct. So we can look at some of the examples from our entity typing experiments where on the left, we're going to have a query, and on the right is a set of observed types, and bold is the maximum scoring type. So we can see things like architectural engineer being predicted with the text mention engineer, baseball player being predicted by baseman, and board members being similar to organizational founders. And we can also look at some quantitative results on this entity typing experiment, where again, here's the goal is to assign the correct set of types to each of our entities. So the first thing that we can see is that the query-dependent methods are performing much better than the query-independent ones. And this makes a lot of sense because the model is able to focus in on only the relevant information rather than some single abstract summary. And we can also see that these methods are actually slightly outperforming the original model, which learned a single abstract vector, even though it used far more parameters to do so. And we also applied these same methods to predicting relationships between pairs of entities. And a nice property is that we can combine this with the neural column encoder we discussed at the beginning of the talk. And this allows us to actually make predictions about entities that we never saw at training time. So just as before, we can take some new sentences at test time and generate column vectors using our neural encoder. And in the original model, we'd be stuck here because we don't have entity pair row vectors to make further predictions with. But by replacing the explicit row embeddings with an aggregation function operating over the observed column mentions, we can generate representations for this entity pair and use that representation to make new predictions about this newly encountered pair of entities. All right, so we also evaluate our model's ability to actually predict the appropriate types for entities that weren't seen during training time. And we see that all of our type-based methods are able to perform similarly to how they perform with entities they did see at training time. And in particular, the query-dependent methods are losing very little accuracy overall. Okay, so another approach for enhancing the way we represent knowledge and context is by expanding the amount of information that we're going to consider when we're trying to reason over a piece of text. So going back to our original document, in reality, the first step for most any NLP pipeline is usually to segment the text into different sentences. And after that, just as before, we're going to identify different entity mentions in these sentences. But some sentences are actually going to contain more than two entities. And the way we typically do something like relation extraction is to actually consider each pair of mentions individually. So we'd have a Bill Microsoft example, a Bill Seattle example, and a Microsoft Seattle example. And the more mentions that occur in a sentence, the more individual examples we're going to break this sentence up into. So this is a bit sad from an efficiency standpoint, since we're going to keep re-encoding the same text over and over and over. But it also reduces the model's ability to jointly reason about the full set of entities at the same time. And what's even worse, or the problem gets even worse in some domains like biomedicine. So if we do the same procedure here, first doing sentence segmentation, in many cases this is going to be fine. So we can still find nice, concise relationships like the one defined in the title of this abstract. But in other cases, we're going to completely lose the ability to even attempt to make a prediction about the relationships. So for example, there does exist a relation between this blue chemical and this red disease, but because they never co-occur in the same sentence, our model is not going to be able to make any prediction about their relationships. And this cross-sentence phenomena is actually pretty common in this type of biodata. So instead, we want to develop a model that simply takes in the entire text context at once and then simultaneously produces a graph of all of the entity relationships within the text. All right, so the initial input to our model is going to be the full text of a paper, title, and abstract. And we're going to first map each token to some context-independent word embedding. In this case, our neural encoder is going to be this transformer architecture. And we're going to use this function to take in our K tokens and contextually encode them. So now we have that we've contextually encoded our entire sequence. The next thing we want to do is predict entity mentions. So here we're going to identify occurrences of both chemicals and diseases. We then project each mention token to both a head and a tail representation, which is whether the mention is going to serve as the first or the second slot in the asymmetric relationships that we want to predict. Then we can get mention level scores as a function between each pair of entity mentions. So for example, we can take the bilinear product using some learned parameters for each of the relation types that we want to be able to predict. And in many cases, we're going to have multiple mention level scores that are actually referring to the same pair of entities. So just as we did before, we can aggregate these mention level scores together, giving us final entity level predictions. And this is important because in this particular data, we only have this type of entity level supervision. We don't actually have mention level annotations for these relationships. All right, so we evaluated our model on the BioCreative 5 chemical disease relation benchmark. And the goal here is to predict these entity level relationships. So our brand model was able to outperform the previous state-of-the-art methods, which were ensembles of neural and feature-based models. And the design of our brand model allowed us to easily add in a large amount of weakly labeled data, which leveraged readily available document-level annotations. We found this gave us a pretty significant boost in performance. And if you're interested in more details, you can check out the paper for details on this data and model. So if we look back at this model, we can notice that we didn't talk about one component. And that is, how do we know which specific entities mentions are referring to? So in our experiments, we assume that we know the particular entity linking decisions. And we got these decisions from some external entity linking model. And from there, we just had to decide whether or not these relation edges existed between these entities. But in reality, these mentions are ambiguous, such that we don't know the specific entity that each mention is referring to. And what's worse is that in many situations, we don't even have an adequate amount of labeled mention level data to train a supervised entity linking model. So just concretely, this would be, in this particular case, the mention of this blue disease could be referring to any of these three entities. And this would be like if the text said Washington, you don't know if it's the state or the president or the school. So the way we're going to approach this is to actually consider all of the possibilities together and think about the fully connected graph minus any edges that we can prune due to things like type constraints. So say we want to get the probability of the existence of this particular edge. So we can actually decompose this a bit into three separate pieces, which is what's the probability that any mention is linking to the first entity? What's the probability that any mention links to the second entity? And then what's the probability that the text is actually expressing a relationship between these entities? And the important thing here is that we can train this model without any mention level entity linking supervision. So all we need to know is that some relations have to be true and other relations have to be false. And we can even negatively sample relationships and treat them as false. In addition to being able to train an entity linking model without any mention level supervision, we also now have a framework for a single model to perform the full AKBC pipeline. So again, this is mention detection, entity linking, and relation extraction. So we evaluated the model's ability to predict entity-level relationships, which again meant that it required both the correct entity linking decision as well as the correct relation decision. And we compared our model that does the linking and relation extraction jointly against two different pipeline approaches. And these pipeline approaches are going to consume hard entity linking decisions from some external model. Other than that, all the model architectures are going to be the same. And the first row here is labeled top candidate takes the most likely entity from an alias table. So this is just based on the actual string of the entity mention. And the second row is going to take linking decisions from some high-performing trained external entity linking model. And we can see that our joint linking and relation model is actually pretty substantially outperforming the pipeline approaches. And this largely comes down to cascading errors, since the model is unable to recover from incorrect hard decisions made about entity linking. And this can really be exemplified well by the much higher recall of the joint model over the two pipeline approaches. All right. So before I move on to discuss some future research directions, I just want to touch on a few of the other related areas that I've worked on but don't have time to go into extensive detail on right now. So I've worked on numerous projects for named entity recognition, including fast models for efficient document level extraction, and methods that train on multiple data sets containing disjoint label sets. I've also worked on semantic role labeling, which is the task roughly of extracting who did what to whom. And we came up with a multitask model that incorporated syntactic information into the self-attention mechanism of the transformer neural architecture. And this boosted the performance of the model quite a bit, especially on generalizing to new domains. And this work won the Best Paper Award at this year's EMNLP conference. And more recently, I've been developing a model for unsupervised parsing and constituency representation that used latent tree neural nets trained with an autoencoder-like objective. And our hope is that we can eventually use these types of models for unsupervised detection and representation of mentions in any domain. And lastly, before working in NLP, I actually worked on several projects in cognitive neuroscience, primarily investigating the role of sleep in enhancing human learning and memory, but also projects for computational modeling of particular memory mechanisms. And this brings me to the last part of my talk, where I want to go into a bit about some possible future directions and how we can take some of the ideas that we've talked about even further in the future. And I think a main theme of the future work here is how we can better represent knowledge in context. And I think a place that makes a lot of sense to take inspiration from is actually by looking at what we know about human memory. So in my future work, I want to incorporate my degree and my past training in neuroscience with my work in knowledge graphs and NLP. And I'm going to first talk briefly about some aspects of human memory that have informed some of my thinking in this direction before tying these ideas back into knowledge graphs. So one may be inclined to think of all of our memories as kind of a single collection made of the same type of thing. But in reality, humans actually have multiple interacting memory systems that are encoding different types of information at different levels of abstraction. So the starkest distinction is really between explicit and implicit memories. So implicit memories are largely procedural or reflexive in nature. So this includes skills like tying your shoes or riding a bike. And they're largely things you don't need to think about for them to happen. On the other hand, explicit memories are encoding things like facts and events, such as how you know the capital of Massachusetts or how you can remember a particular vacation you were on. And kind of the main reason that we know about this particular distinction is because of this person. So this is Henry Molaison, also known as patient HM. So in order to treat his debilitating seizures, doctors removed a piece of his brain. But unfortunately, they ended up removing this piece, which was his hippocampus. And this did address his seizures, but after the surgery, he was unable to form any new memories. So however, doctors ran an interesting experiment where HM had to sketch the outline of a shape, but he could do so only by looking in a mirror. So this way, all of his actions were reversed. So this made it both a hard task, but more importantly, a skill that he didn't have before his brain injury. So even though every day he wouldn't remember the task or the fact that he'd just done it yesterday and the day before that, nonetheless, he got better and better at this task over time. And this was really the first most important evidence of humans having multiple memory systems. And because of that experiment and future work, we learned these memory systems are actually mediated by different brain regions. So without a hippocampus, HM's explicit memories were terribly damaged, but his implicit memories were largely intact. And from the perspective of the type of knowledge representation that we've been talking about, I think a more interesting distinction is between two different types of explicit memory. So this would be semantic and episodic memories. So semantic memories are really encoding abstract world knowledge and facts, such as the fact that a dog is a mammal and a mammal is a type of animal. And importantly, these memories are not directly tied to any individual experience, but are instead abstract generalizations. On the other hand, episodic memories are the individual experiences themselves, as well as the rich context that they're made of. So instead of the abstract notion of a dog, your episodic memories are going to contain information about interactions you had with some specific dog. And while semantic memories are going to have facts like dogs being fast runners, your episodic memories are going to contain specific times you saw a dog running fast, as well as times you saw dogs that didn't run very fast. So the main idea I'm trying to get at is not that we need to make our knowledge representation system strictly biologically plausible, but rather as we look to improve our methods, we can consider and take inspiration from systems that we know are very good at knowledge representation and reasoning. So from the standpoint we've been discussing, semantic memories are really analogous to current knowledge bases. So these are encoding abstract facts without any particular grounding in a specific instance. And from there, we can think about how we can leverage the idea of something like a rich contextual episodic memory system for helping us represent knowledge in context. And in a way, this is really the data itself, or the text, where here knowledge is grounded in specific instances of information within a particular and continuous discourse, including the full range of the surrounding context. So what might something like this actually look like? So we can imagine for a piece of text extracting some relationships over sentences. And these could be encoded using some semantic framework like semantic role labeling or abstract meaning representation. And this would give us some sentence level graphs. We can then build these up hierarchically, connecting sentences and paragraphs, and connecting paragraphs up, and finally building representations over full documents. And we do the same procedure over many different documents, and then continue connecting these pieces upward to the level of a full corpus. And really, as we're building this hierarchy, what we're doing is constructing this continuum of abstraction where specific concrete instances lie at the bottom and abstract knowledge is at the top. And something like this would give us not only the type of abstract knowledge we currently encode in knowledge bases, but now it's going to be grounded in these specific events, each encoded within the rich context that they were originally observed in. So another type of context that's missing from current knowledge representation modeling is the concept of time. So nearly all research in this area focuses on knowledge and data from a single time slice. But this neglects the fact that new information is constantly being produced and knowledge is constantly evolving. So this is another area where our understanding of human memory could inform methods for integrating this type of information. So one aspect of episodic memories are that they're inherently organized in a consistent timeline. And we can think about how we could design models and representations that also have some intrinsic property of time built into the representations themselves, because ultimately we want models that can not only evolve over time, but can also reason about the temporal nature of events. So we'd like, as new information comes in, we can add this new information to our memory systems. And this includes not only adding knowledge, but also updating our beliefs in the face of new information. And this is a property common in domains like science, where new experimental results are constantly updating what we know to be true. In addition to science papers, the same type of information stream could be seen in domains like news and Twitter. And I think these same types of principles could be beneficial there as well. But what we've described so far, knowledge is essentially one-directional. So as new information comes in, we can add this to our store of knowledge. But what we really want to do is use this knowledge to interpret the new information that we encounter. And again, this is something that humans do. So when we encounter some new information, relevant memories are retrieved from long-term storage. And then this prior background knowledge is used to actually decide what this new information means, how it relates to all of the other knowledge that we already possess. In some ways, we can again think of this as expanding the context for which we're using to interpret information. So that is, we're looking not just at the information itself, but now we're looking at our complete understanding of how it relates to all of our past knowledge that we've already acquired. And we can imagine how this would be not just a single-step procedure, but instead how we can have a short-term storage for working memory, allowing us to iteratively retrieve, integrate, and reason over various concepts and memories. And I think this type of reasoning over existing knowledge is going to be crucial for advancing these methods going forward. And this includes not just includes the types of reading applications that we've been mostly talking about, but also things like dialogue, where there's this dynamic, evolving discourse being built up iteratively over time. And so far, I've only talked about language and text. This is really for two main reasons. So language is really closely entangled with the way we represent knowledge, both internally and also as a society. And it's also an excellent source for finding knowledge, since we've encoded quite a bit of it on the internet, for example. But these methods aren't really restricted to language and text alone, and they really shouldn't be. So there's also extremely valuable information in other modalities, such as images. And much of this knowledge isn't even going to be adequately expressed in text. And we can imagine embedding these images into the same unified semantic embedding space of knowledge that we've been constructing. This could give us an even more expressive, multimodal representation of knowledge. And this way, the context has expanded even further beyond text or language alone, and is now being further grounded in properties of the physical world. And in the same way, we can use this information to reason about the contents of new images, to try to understand what they really mean on some higher level in relation to our other existing knowledge. And a particular domain that I think this multimodal knowledge would be extremely valuable in is in common sense knowledge. So images are really a natural way of extracting information about the world that may not be expressed in text. So this can be things like interactions of objects as well as their physical properties. And reasoning over this rich unified graph like this could help us get closer to really understanding what's happening in a piece of text. Okay, so this brings us to the end of the talk. So what I presented here were methods that I've developed for representing knowledge that incorporate neural embeddings with ontological structure. And I think these types of methods can really help us push the depth to which our models can understand language and also represent knowledge as a whole. So these powerful contextualized neural representations can capture fine-grained semantics, while a greater level of structure can serve as a scaffolding for knowledge. This can help for organizing the beliefs of our models, easing the burden on reasoning algorithms, and serving as a ready store of background knowledge to influence the interpretation of new information. So before wrapping up, I just want to thank my various excellent collaborators on the projects I presented today. And with that, I'll be happy to take any questions that you might have. So thanks.
We have time for a couple questions.
Martha?
So I loved your document graphs. Have you thought about trying to use co-reference? Would that help? Is it so noisy that it just makes things worse?
Well, I think ultimately we'd need a mechanism of co-reference to be able to kind of link together these different sources of information. And I kind of feel like that itself is like a really kind of unsolved problem in itself that is arguably one of the hardest, if not the hardest, NLP problem. But I think that inevitably we need to be able to, if we want to actually understand the full piece of text or understand all the text, that's kind of an inevitable piece of the puzzle. Because right now, the entity linking, you're often getting the easy ones, right? The kind of non-easy ones are also really important, though, especially even just linking together adjacent sentences and things like that. Yeah.
And how accurate would it need to be useful?
I guess it depends on what the end goal is. So I think even like even current kind of knowledge-based construction systems are only so accurate, but they still, if you run it on enough data and you have enough kind of tolerance in your end task, they can still be really useful. So I think it would depend on what it is you want to do with it, whether you can say how accurate it needs to be useful. Because you could also imagine, even if you tune the precision really high on something like CoRef, because it's hard, if you run it over enough text, you're still going to be able to gather quite a bit of information. So I think it kind of depends. It depends.
So can I ask you a domain-related question? So when scientists write in the journal articles that you were talking about, they don't think of those articles as data. They think of the stuff that came out of the instruments or whatever they were measuring as data. And often the problem in interpretation and making sense of all that stuff is the bottleneck is the human being thinking about it and hypothesizing stuff. That data often takes the form of entities and there's ontologies. Here's a list of 20,000 proteins, plus usually quantitative, although sometimes other data about them. How would that fit into your vision of not just images and text, but real sort of more scientific data as a
Yeah, I kind of think of this as kind of just another modality in a way, and we should really be kind of utilizing all of the information we have. So you can think of, I guess it would depend on the particular type of data, but you could think the same way you could imagine an image being the representation of an entity and having some sort of learning that kind of merges these in some way, some properties about an entity, whether they're quantitative or what have you, can also be utilize these same shared representations. So in some ways, it's almost, like one way to represent this is almost like a type. So we know Barack Obama was a person. You could say, we know this protein has this physical property. So you can have, you can imagine putting some mechanism in for treating that as just another object within this kind of representational space.
But those particular qualities really depend highly on the context. Right? Whatever, I measure a bunch of genes in some cell after it goes to a drug or after you're sick or something like that. So it really needs to use the context piece in a way that's sort of different than just here's an image that has a dog in it.
Right, definitely. Yeah, and I think even like the representation, let's talk about the graph because it's slightly easier to think about. We're just talking about like binary relationships in a way. And as we're kind of talking about a bit, there's really not enough context to actually even encode a lot of the properties. I mean, even simple things like I was talking about a rat or a human, but you're talking about an even greater context. So I think this in itself is an open question of what is the appropriate kind of representational frame in a way that can actually represent these different pieces. So I think that I totally agree that that's a really important question, and I think it's an open question in a way.
Give one like text take on it. So how do you deal, or do you, especially with tables and things like that in documents?
Yeah. So
just as sentences or images?
Yeah. So in this particular work, we're not dealing with them at all. So we're really only looking at titles and abstracts. It's partly due to paywalls and things. But there are people that also work on extracting the table's information directly, and kind of, you could imagine utilizing that as more of like a quantity or property like you're describing. So I guess currently we're not dealing with that, but that is really useful information that I think ultimately in the final product of end goal, you'd want that, yeah.
So I think we'll cut it off there. We still have some cookies and refreshments, and Pat will be hanging around, so if you have more questions you want to follow up.